Good afternoon, everybody. My name is Dr. Klaus Wiemer. I'm the lab director at Poma Fertility. I'm also the scientific director, and I have been the lab director here at Poma Fertility now for a little over 5 years, and have been a lab director in human IVF since 1986. I've been involved with Life Global since the inception and was involved in the formulations of the global media family as well as the other medias that are used as well. So we have quite a bit of experience in the use of global media. Today we're going to talk about the impact of protein supplementation type on embryo development as well as ploidy type. So this study took over a period of about 5 months, and we only utilized good prognosis patients with a high order of sibling zygotes, so that we were able to reduce the amount of patient variability that we were going to have in this study. We excluded all donor eggs and we excluded all testicular aspiration cases. So in other words, autologous oocytes as well as ejaculated sperm were used in this. And so basically what we were trying to do was we were going to aliquot zygotes to 2 different types of culture systems. Global total medium is a medium that contains 4.4 milligrams of HSA, but it also contains approximately 0.6 milligrams of alpha and beta globulins, whereas global LP is the same global-based medium, but it's supplemented with 5 milligrams of human serum albumin, also referred to as HSA. And so this media is devoid of any globulins. So the objective of this study was to see if pure human serum albumin or HSA was going to function as well as a global-based media that was supplemented with an alpha and beta globulins. So we really wanted to see, does protein impact embryos? So in order to do this, we had to really utilize a very strict time period. And you can see in the table that for embryos on day 2, they were evaluated 48 plus or minus 1 hour post-retrieval. So the time of egg retrieval is always referred to as time 0. So if, for example, if the egg retrieval is at 9:30 on a Monday, we would look at those zygotes at 9:30 on Wednesday. That would constitute the day 2 evaluation. Well, following along that same idea, on day 3, we looked at the embryos 72 hours plus or minus 1 hour post-retrieval. And again, we looked at them on day 5, 120 hours plus or minus 1 hour. And we did this so that we could very strictly look at the effect of the protein supplementation on embryo development. The other thing that's of interest is that we looked at the embryos on day 6 first thing in the morning. Now, we did this for a couple of reasons. Significant number of patients in this study were embryos that had the embryos that were going to undergo embryo biopsy. So we wanted to look at the embryos early enough on day 6 so we could avoid having to biopsy hatched blastocysts. So we had a total of 100 patients in this study. The age was almost 35 years of age, plus or minus 4.6 years of age. The total number of zygotes in the global total, referred to as GT, was 769. The total number of zygotes in the low protein was 745. So we retrieved a total of 2,238 oocytes, of which 1,685 were fertilized. So if you break this down into the type of fertilization, you can see that the majority of the oocytes were fertilized using conventional means, approximately 70.1%, or 1,181 of those zygotes were created using conventional IVF, in comparison to only about 30% of the zygotes, or 504. So you can see on the far right that we had a significant number of embryos, starting with about 1,514 zygotes on day 2, and you can see that we whittled this down to about 880 embryos on day 6. So there was a sizable number of embryos that were included in this study. Again, these were patients with good prognosis. We wanted to reduce the impact of oocyte variability, and we ruled out any severe male factors. So as far as how did we process the oocytes from the time of retrieval, Well, we use step-down protocols in our IVF clinic, and we trigger when the patients have anywhere between 2 to 3 18 millimeter follicles. And in most of the instances, we used 10,000 units of HCG. In some instances where we thought perhaps a patient might be subject to ovarian hyperstimulation, we used a combination of Lupron and HCG. So the oocyte retrievals occurred 36 hours plus or minus 1 hour from the application of HCG. So excess cumulus cell, the oocytes were recovered and held in global collect. And then what happened was in global collect, we would then dissect the oocytes, remove the extra cells, and then we were placing anywhere from 1 to 3 cumulus oocyte complexes in each drop. And then oocytes were fertilized either using IVF or ICSI, and this was based solely upon sperm parameters resulting from diagnostic testing. And in our laboratory, we use an acrosome reaction assay to determine how many sperm we can cause an acrosome reaction, coupled with strict criteria morphology. We use a 24-hour motility assay, as well as a hyaluron binding assay. So in all cases, we try to avoid ICSI whenever possible. And so ICSI tends to be reserved only for the cases that are truly a male factor. In those cases where we had to do ICSI, though, we used global collect, which was supplemented with 5% human serum albumin for the injection process. Now, the reason why we use global collect is that global collect is a global-based product that is buffered to work at 37 degrees. So when you look at the pH of global collect with albumin in it, you get a pH of about 7.25 to 7.30, which is a perfect pH for oocytes. Again, during the ICSI process, we don't want to stress the oocytes any more than needed. So not only is it collect buffered with HEPEs, but it also contains all of the amino acids. And these amino acids further help stabilize the intracellular pH. Amino acids are very, very good at doing this. So ICSI or conventional insemination in all cases were performed 3 to 6 hours post-egg retrieval. So embryo culture details are described as here in this slide. So all embryos were cultured in humidified triple gas incubators. In our laboratory, we use predominantly planar benchtop incubators. These incubators are checked every day for temperature and to ensure that they're functioning correctly. Now, the pH of the media we had previously established through trial and error using tanks with different amounts of CO2. And so really we're not so don't put so much emphasis into the percentage CO2 rather in the pH. So in all cases, the pH of the fertilization media is 7.3, whereas the pH of the media for embryo culture ranges somewhere between 7.26 and 7.28. And the pH values in our laboratory, what we normally do is we check pH values every week. We do this for a couple of reasons, just to make sure that our gas quality stays the same, and it also helps us ensure that the incubators are functioning correctly, since it's easy for the gas lines on benchtop incubators to become occluded for a variety of reasons. The other reasons that we would check pH would be whenever we had lot changes that came in. So whenever we had a lot change, we would always check the pH. All embryos were cultured in universal GPS dishes using washed lifeguard oil. We washed the oil at a ratio of 1 to 4. This is described in great detail in the white paper, which you will also be given a copy of as well. All of our dishes are incubated for a minimum of 19 hours prior to use. And we found this through a study that we did using a continuous pH measuring device. We found that with the viscosity of lifeguard oil, that basically we had to have our culture dishes in the incubator for a minimum of 19 hours, or else we could have slight variations in the pH within the microdrop. So we've now made it a policy in our laboratory to have all the dishes in the incubator by 1 p.m. so that we can use the next day the dishes and know that the embryos or the dishes have had at least 19 hours to equilibrate. Along that same line, we're using 12 mLs of oil, and our microdrops are anywhere between 15 to 20 microliters of the respective media, and it's done in an underlaid fashion. In other words, we put 11 to 12 mLs of the washed life oil into the dishes, and then we allow them about 2 to 3 minutes to anneal to the bottom of the dish, and then we put our microdrops in, and we use a fire-polished 9-inch pipette, a sterile one, that has been previously rinsed with HTF. And the embryos in this study were changed to nude culture dishes on day 3. In our laboratory, we routinely do uninterrupted culture, but for this study, we decided to change the embryos on day 3 to fresh dishes, again, to reduce any variability from environmental issues. We will discuss thoughts on my thoughts we will go over as far as uninterrupted embryo culture. So media preparation, and we're going to have a video slide after this slide that's going to go into great details for media preparation, but just in brief, we do not aliquot any media in our laboratory. We do not aliquot it into 4 ml tubes or anything like that, like a lot of laboratories do. And we don't aliquot out medias because we're simply very adverse to introducing any kind of variables that can impact how the embryos grow. Namely, we worry about the effects of plastic wear and how much variability there can be in the quality of the plastic even within one lot. It's mathematically impossible to test enough of your plasticware in the lab to not have subsampling errors. So we simply avoid this by not aliquoting. So what we do though is you have to aliquot media at some point into a dish. So what we do is we calculate how much culture media we're going to need for that day. So we take the appropriate size dish, either a 35 or a 60 millimeter nunk dish, and then we rinse that dish with the appropriate amount of media. Basically, we fill the dish with culture media, and it's just neat HTF. It does not contain any protein. We allow that media to sit in that dish for a few moments, and then while that dish is sitting there with the media in it, we go ahead and rinse the pipettes that we're going to use for drop making. And so then what we do is then we remove that media. Our thoughts are that the combination of culture media with some of the salts that are present in HTF, and really in all culture medias, will help chelate any of the potential molecules such as benzene, aldehydes, things like that, which are commonly found in glues, which are used to make these Petri dishes. So once we've rinsed the dish, then we aliquot out the desired amount of media, we make our microdrops, and then we throw away whatever media is left over. Just to be clear, we do not wash or rinse the GPS dishes. And the reason for that are a couple. Number one, if you did rinse the wells, it would make it problematic for your culture drops to sit in there because once the media is on there, it leaves a slight coating and it would make it very hard for the media to come back to that unless you left enough of a footprint. We've decided not to go that route because the GPS dishes are manufactured to a slightly higher standard than other plastic dishes, and these dishes are also mouse embryo tested. As I stated earlier, we allow the oil to anneal to the bottom for 2 to 3 minutes, and then we make our microdrops. And we make our microdrops in this fashion, and you're going to hear more about this in the next video clip. But we do this because when you put the oil first and then the microdroplet, the shape of the microdroplets are really nice and round, so you get minimal refraction of the light, and you can get really nice visualization of the embryo. So you want to take advantage of the way these GPS dish wells are made, since you have a little less plastic, so you tend to have less shearing of the light in that way, and you have much better looking pictures. So basically, our whole culture system methodologies of making dishes, what we're trying to do is reduce the impact of plastic on culture system by controlling as many variables that we personally could introduce during dish making. So by removing aliquoting out or holding media in transient tubes prior to that, we simply are removing the effect. So the next, so what you're going to see now is a video clip talking about how embryos are cultured, or how our culture dishes are prepared. Welcome everybody. I'm really glad that you're getting to see how we do dish preparation using global total LP. So right now my colleague Ryan Woodyard is going to be putting oil in the GPS dishes. The reason why we do the oil first is to allow the oil to anneal to the bottom of the dish. Then Ryan is going to make the actual dishes himself. While Ryan is prepping the dishes right now with oil, a couple of things that occurred already in the interest of time is that there is a small 35 millimeter dish that's in the hood as well. That dish has already been rinsed with culture media, and that dish was rinsed with just HTF that did not contain any protein. The reason why we did this was that we know that sometimes there can be some surfactants that are present on the surface of these plastic dishes that could potentially impact embryo development. So we want to remove any effects that oil, or that I should say that the plastic may have on embryo development. So we have found that by just simply rinsing the dish with straight HTF, that the water solution as well as the salts that are present help lift any potential contaminants. And we found this by looking at mouse embryos from years past, that when we don't rinse plastic dishes, that we get much more erratic cell counts in our mouse embryos. The other thing that Ryan did earlier was to take the Pasteur pipette and fire polish it and rinse it with culture media, again with neat HTF. And the reason why we use these Pasteur pipettes is that we feel that glass is a more inert subject to make microdrops with. In other words, we're less likely to introduce variables. We're not as concerned with the exact size of the microdrops. We're more concerned that the vehicle used to deliver the microdrops is nice and clean and does not have any potential contaminants that we are adding to the microdrop culture system. So Ryan has now placed enough media to make our dishes. The GPS dishes we normally would label with a patient's last name, birth date, and another unique identifier. So right now what Ryan is going to do what we would call media underlay. So the oil's already in the dish, and so now he's going to make micro droplets of approximately 25 microliters. Now the reason why we do them like this is that we have found if we put the drop first and then the oil, that the drops don't have a really nice plumped up appearance. We found that by putting the oil first and then adding the media, what it does is allows the drops to have a really nice plump appearance. The reason why we feel this is important is that the GPS dish is built to maximize the optical visibility of the embryo. In other words, it's the drop where it sits has got less plastic, so you have less optical distortion caused by the plastic. And so, and if you plump up the drops now in the manner that Ryan is doing this, what happens is that you get a lot less light refraction. So as you can see, Ryan is just making each drop. They're approximately the same size. And then you saw in the previous dish that the center drops are filled pretty much to capacity. Now it's really important when you're developing your microdrop system that you use enough oil. So we use approximately 11 to 12 mLs of lifeguard oil that's been previously washed. And the reason why we use 11 to 12 mLs is that we have found in conjunction with 25 microliter droplets that we have at least 1 to 2 millimeters of oil over the apex or the top of the droplet. We found from our previous research that we need to have that much oil over the top to prevent any significant amount of evaporation from the microdrops. So again, we use somewhere between 11 to 12 mLs of Lifeguard oil. We preferably like the Lifeguard oil because it's a heavier oil. So what we have found is that when we're taking the dishes out to evaluate them, we have less pH drift, less temperature drift when we're evaluating the embryos. When we evaluate embryos, we typically do this with 2 people, and we only put 1 embryo per drop. So typically we can grade embryos in less than 5 minutes. We use washed oil because we feel like it's a good practice by equilibrating the oil with the salts that are commonly found in our media. We feel that we also get partial equilibration of the oil with these salts that are commonly found in the culture media. So again, you can see that Ryan is just making 1 dish at a time. We do this so that he can take a lot of time and attention. You can see that in the previous dishes he makes each drop, and that he's removing any oil bubbles that may be on the top that again would impact image quality. So again, just to reiterate, 11 to 12 mLs. We underlay 20 to 25 microliter drop, and we do this to maintain the optical abilities to look at the embryos as best as we can. So I hope that you enjoyed that video clip and hope that that helped remove any questions that you have. But basically how you saw in that video clip how Ryan was prepping dishes, and this is how we prepare all of our dishes here at Poma Fertility, whether it's culture dishes for embryo culture or culture dishes for holding oocytes on the day of egg retrieval. So one of the things I wanted to take here was to talk a little bit about some of my thoughts on uninterrupted culture, because really global media is a media that would allow us to do this. And so when you think about culturing in an uninterrupted system compared to a sequential or an interrupted system, you have to think about completely different culture systems, and you have to think about the environment. And the reason why I say that is that uninterrupted culture systems work really best in labs that have really high quality air handling systems, where you have banks of charcoal filtration as well as banks of activated potassium permanganate. Because really, these are the only way that you remove virtually all of the VOCs, the volatile organic compounds, from the air. And so when you make your culture drops too, the other thing that you have to do is you got to make sure that you have enough volume of oil over the top such that you're not going to have any evaporation of the water from the media. So it's really important to do multiple trials in your laboratory. If you're wanting to go to an uninterrupted culture system, you really have to work out the specificities for how much oil you need in your dishes, how big your culture droplets should be. You want to verify that there's no evaporation going on in your lab. And so these are the things that you would do before you ever even cultured any embryos in an uninterrupted system. And then you would probably want to do sibling zygotes, changing over half others that you culture long term. And the reason why we go to that great effort is that you've got to understand that oil is really the sink for VOCs. It's the same thing as leaving a sponge in the bottom of your sink at home. Eventually that sponge becomes saturated with water, and then the water starts to leave the sponge. Well, think of oil being the same way. If your laboratory has a lot of VOCs in it, eventually the oil is going to become saturated, and at some point those VOCs are going to move out of the oil into your microdrops. So if you're going to use uninterrupted systems, you want to make sure you perform trials to make sure that your microdrops are not evaporating. And that's why we emphasize anywhere from 1 to 2 mLs of oil over the top. So the question is often, should we do uninterrupted culture in only humidified incubators? My personal thoughts are yes, because we have found that even in benchtop incubators with 90% humidity, that if you don't have a large enough overlay, you do get evaporation of media. or water, I should say, from the microdrops. And you do get some evaporation no matter what. So I've never done this study in an incubator that's not humidified. What I would imagine, though, that the humidity levels would be very low, and therefore the potential for water to evaporate is great. We did find in our lab, though, that if you did not have enough of an oil overlay, that the media evaporated enough so that the osmolarity reached lethal toxic levels. So this is something that you definitely need to look into. So at the end of the day, if you're really unsure as to how pure or not pure your lab environment is, it's really easy. Just make a dish of the same media on day 3, change over your embryos on day 3. If you're ever faced with a situation where you believe your lab's been insulted with a lot of VOCs for a variety of reasons, say there's a lot of fires in your area, or they're paving parking lots around you and they're using all these sealers for the pavement. I've actually had those things happen to me in the past, and we actually moved the embryos to fresh dishes every day, and we were able to get past this period. So oil can be your friend to a certain point, but once oil becomes saturated, it's not going to be your friend anymore, in the sense that now that will be your major source of VOCs in the lab. So what about oils that are used? There right now are many, many types of oil that are out there. There's oils that are paraffin, there are oils that are mineral-based, and there's oils that are very light to very, very heavy. So oils, in theory, should be compatible with all of the culture medias that you use. In other words, you should be able to use VitroLife or Sage oil with Life Global media products, but you need to understand very well that all oils are not created the same, and you have to become knowledgeable about the oils that you use. Namely, how fast do my oils equilibrate with CO2 so that they provide a solid buffer against pH change, and also how fast does this oil warm up? Because remember, the oil in a sense acts as a blanket to keep your microdrop temperature stable. So it's really important that once you settle on an oil, that you spend enough time working with this oil to see how fast it warms up, how fast does it take for your microdroplets to equilibrate, and then also when you take the dishes out of the incubator, how fast does the gases begin to leave the microdrops and the oil, and also how fast do your dishes begin to warm up. So these are things that are really important to look at. In theory, all the oils should work really well, because the oil properties are going to really impact rate of temperature changes during dish equilibration and embryos evaluation. This is something you have to be cognizant of. In other words, a light oil is going to warm up and equilibrate with CO2 much faster than a heavy oil, but conversely, a heavy oil is going to off-gas and lose its temperature much slower once that dish is removed from the incubator system. So really depending on how many embryos you culture at a time, how many embryos you have in a dish, do you use other people to help you evaluate embryos? These are all the things that you should take into account to determine what type of oils that you use and how often you grade embryos. In our center, we believe that washing oil is a benefit. We don't really see any reason why not to. We know that some of the components that are used in making culture media, whether it's HTF or the basis for Life Global, there are salts in here. And we also know that some of these salts are soluble in oil. And so therefore what we want to do is in theory, by washing the oil, we're trying to do a couple of things. We're trying to equilibrate the oil with as many of the oil-soluble constituents defined in the media as possible. Because remember, oil is very good at taking things out of media. Well, it can also remove some of the good products in the media as well. Now, oil also, because depending on where it's made, how it's handled, is susceptible to peroxidase radical production. And so we find that it's a safeguard to simply wash the oil, because it has been shown in the literature that washing the oil will remove these radicals, and it just provides an additional safeguard. Especially since we are trying to do uninterrupted culture and we are growing embryos to day 5, so we know that the oil is an important variable that can really have a large impact on how well our embryos develop. So we believe that washing oil is an additional safeguard. We've never yet seen a study that shows that washing oil is bad for embryos. So now what we want to do is kind of bring this conversation back to our study, where we're actually now going to go how our embryos looked on day 2. The red graphs represent GT, or global total. Again, this is a media that contains alpha and beta globulins. The blue bars are the low protein. Again, just a reminder, these contain no globulins. This is just pure HSA. And the first thing we want to look at is that in both groups, we had a high number of embryos that made it to the 4-cell stage 48 hours post retrieval. And the reason why this is an important benchmark in our lab is we have found that about 70 to 72% of the embryos that become blastocysts on day 5 and day 6 are 4 cells 48 hours after the egg retrieval. So we use the number of 4 cells on day 2 as a benchmark. And the fact that we have, over 50% in both groups is good. The other thing that you notice is that the percent embryos with less than 20% fragments is very high in both groups, although it is statistically, there is statistically more embryos with less fragmentation in the global total group, but both groups nonetheless show a very high proportion of embryos with little fragmentation. You can see that multinucleation was slightly higher in the low protein group than in the global total group. And again, the percentage of embryos that had perfect symmetry was 45.4%, which was significantly higher than the 39.6% observed for embryos grown in the low protein. So now when we looked at our embryos 72 hours post-development, again we can see that overall the rate of embryo development in both media types is very high. For example, that we see that the percentage of 6 to 12 cell embryos is, over 80% in both groups. Now the reason why this is important is that we have found that embryos more than 6 cells, somewhere between 8 to 12 cells, 6 to 12 cells, that the vast majority of our blastocysts come from those. So obviously the more embryos that are in that range on day 3, we can expect a greater percentage of those to become blastocysts. And we can see that indeed over 90% of them in both groups were that. And here we can see there's just a slight percentage higher in favor of the global total for percentage of embryos that were greater than 6. Embryos that had less than 20% fragments, we see here that again over 80%, in fact 88.7% in the low protein compared to 91.2% in the global total. And if we look at the percentage of embryos that had perfect symmetry, we could see that 42.8% in global total, and in low protein 37.7% had perfect symmetry. And the reason why symmetry is important is we have found from looking at our data that the percentage of embryos that are symmetrical have a greater percentage of becoming blastocysts than those embryos that exhibit asymmetrical or severely asymmetrical properties on either day 2 or day 3. So again, overall, both culture systems are providing high levels of embryo development all the way till day 3. What about compaction? Now, one of the beautiful things about working with a global-based media, as in compared to the sequential type medias, are that when you culture embryos in global media, these embryos are exposed to all of the amino acids, both the essential and non-essential amino acids, whereas that is not true when you're culturing in a sequential system. And what we know now is that when all of these amino acids are present, these amino acids work in conjunction with each other in improving the incidence of compaction. In other words, the rate of compaction in embryos that are cultured in sequential systems, it's much lower than when you're culturing embryos in both essential and non-essential amino acids. And global media contains both groups. So you can look at our data and see that regardless of the culture system that they used, that over 50% of the embryos show some sign of compaction by day 3. And compaction is an important characteristic. We find that a much greater percentage of embryos become blastocysts if they start to at least initiate compaction by day 3. Conversely, you can see on the far right there that over 53% of the embryos, or 53.5% of the embryos in the low protein were showing compaction between 6 to 12 cells in comparison to 59.4%. which was significantly higher for those embryos in the global total. So it does appear like perhaps some of the globulins were helping at least the embryos with compaction up to this point on day 3. Interestingly enough, we noted that only about 3.3 to 3.7% of the embryos exhibited full compaction. In other words, you cannot really make out the blastomeres individually from each other, more analogous to what you would see on day 4. So again, if we look at this just shows the data in a different format. There were 747 embryos in the global total compared to 724 in the low protein. 58.1% were showing compaction, which was significantly higher than the 52.1 exhibited in the low protein. There was no difference in the incidence of complete compaction. And again, the percentage of 6 to 12 cells showing compaction did show some favor towards the global total. So that's really the data all the way for these embryos all the way up to day 3. So it'll be interesting to see now what happens after day 3. So this data shows blastocyst development. The group of bars on the left show day 5, the middle group of bars are day 6, and the far right is the overall. And we can see that pretty much overall that the percent of blastocyst development was 46.8% in global total compared to 48% in low protein. That was not significantly different. In fact, it was virtually the same. However, the percent of embryos that were of high quality in global total was 64.7% compared to 58.2%, which was just slightly higher. The percent day 6 embryos that were present in global total was 34.5 compared to 29.6. And of high quality was 35.9 in comparison to 30.9. In other words, these are embryos that were not blastocysts on day 5. They just needed more time to get to the blastocyst stage. Overall, blastocyst development in global total was 58.6% in comparison to 57.2% in the low protein. And the overall high quality blastocyst production was 66% in global total and 61% in the low protein. So the way we define high quality blastocysts, if we use the Gardner system, these would be embryos that possess at least an A or a B in their nomenclature. And these are embryos that are blastocysts or greater. In other words, these are blastocysts that we feel can be utilized for either embryo transfer, cryopreservation, or biopsy. So we wanted to be able to tease out the percentage of embryos that were usable. And we can see that the usability rate of embryos that became blastocysts was high, 66 and 61% respectively for those media types. So again, from numerical here, we see that there was 727 embryos in the global total, 713 in the low protein. And we see the blastocyst development rate was 46.8 and 48% respectively for the two groups. And we can see that the percent embryos that became blastocysts was slightly higher in the global total compared to the low protein, 64.7 compared to 58.2. And again, for day 6, we can see that virtually the percent of embryos that became of good quality was 35.9 compared to 30.9. So there was really no impact there. So what about ploidy rates? In our clinic, the majority of the patients that went through were patients that were doing embryo biopsy. In other words, these were patients that did not have a transfer. So here we see that, again, we biopsied about 154 embryos out of that group. The other embryos were either from patients who did not have embryo biopsy or were embryos that were not of quality to freeze. The euploid rate was 51.3% for global total compared to 58.4% in the low protein. The percent aneuploid in the global total was 31.8% compared to the 31.1%. And the mosaicism rate in the two culture system was 15.6% in global total as compared to 9.9% in low protein. So there was really no impact on the type of protein supplementation that we utilized on the percentage of blastocysts that were considered euploid, aneuploid, or mosaic. And one really wouldn't think that the protein source would impact, but it was certainly well worth looking at. So here, this bar graph shows also the percent ploidy rates, and we can see that the bar graph shows that everything was very close, that there was really no impact at all on albumin type. If we look at day 6 embryos, in other words, these were embryos that we were able to biopsy on day 6. We biopsied 125 embryos in global total, 102 in the low protein, and the results were as follows. 46.4% of the embryos in global total were considered euploid in comparison to 48 in low protein. 35% were considered aneuploidy in both groups, and 16% were considered mosaic in global total, and 12.7% in the low protein. So we can see that the culture media, again here on day 6, did not impact the rate of euploid, aneuploid, or percent mosaic in either of those systems. So here again, the data and the bar graph shows, again, that the data, the development of euploid embryos is very, very similar, as well as the percent that are aneuploid and percent that are mosaic. So overall, when we combine all the data, 49.1% of the embryos that were biopsied, of embryos that were cultured in global total, were euploid in comparison to 54.4% for embryos that developed in low protein. And aneuploidy rates were virtually the same, 33.3 versus 32.7 for global total and low protein respectively. And again, mosaicism rates were 15.8 in comparison to 11% in global total and low protein respectively. And ploidy rates overall, again, this is just the table showing you exactly what we showed, that basically that neither one of the protein types had an impact. And in fact, we were really pleased with the percent embryos that were euploid in both cases. We feel that both culture systems work very, very well. And at least for this patient population, that the percentage of embryos that were euploid was very satisfactory. So a small percentage of these patients actually did have embryos that were transferred, as well as embryos that were frozen but were not biopsied. So this data represents patients who had embryos transferred from both groups. So the biochemical pregnancy rate for patients whose embryos were transferred or cultured in global total was 84%, and it was 80% in low protein. The clinical pregnancy rate, and we define clinical pregnancy rate, is a visualization of a gestational sac and cardiac activity with 2 ultrasounds. So these are pregnancies that we feel are they're past the miscarriage rate and most likely are going to be able to go to term. So again, the clinical pregnancy rates for embryos grown in global total was 69.2% compared to 70% in the low protein. And we felt really good about this. Anytime we can get pregnancy rates over 50, 60%, we feel like we're doing a good job in the lab. Again, here, this data just shows this, the number of patients. So the number of patients who had transfers in global total was 26. The number of patients who had a transfer in the low protein was 20. So it represented a small number of patients, but nonetheless, the results were favorable in this part of the study. And if we look at implantation rates, percent fetal sacs was 60.6% compared to 63.9% in global total versus low protein, and percent fetal heartbeat was 60.6% in global total in comparison to 63.9% in the low protein. So again, we felt really good about the outcomes that we have. I do want to note that in this data, we did omit 2 patients because a patient didn't have the best embryo development, so we did transfer 1 embryo from global total and 1 embryo from low protein. So it would be hard to determine which embryo implanted, so we omitted that case, those 2 cases to keep the data clean. So again here, percent fetal heartbeats, 60.6 in global total and 63.9 in low protein. So again, implantation rates are excellent. Anytime we can get implantation rates over 50, 60%, we feel like the laboratory is doing its job. We feel that the culture systems are good and that the quality of the embryos that we're producing are competent. So after we had done the sibling study, we then proceeded to just try culturing embryos in just low protein and see, okay, we've had some good outcomes, but we didn't transfer that many embryos. So now let's just transfer out of low protein. And the reason why we had just chose the low protein was that we had had a long history of embryo transfer with the global total, and it felt really good about that. Now we wanted to see how good of outcomes we would get just using low protein. So the data that I'm going to present next was from 78 retrievals, and these were patients that were cultured during the time from January to March of 2019. And the data that we'll present will summarize embryos in culture, transfer, and pregnancy rates. So again, we excluded egg donors, and we excluded microsurgical testicular aspiration. So in other words, these were all autologous. The patients it was their own oocytes, and all the sperm was ejaculated sperm. There was no surgically retrieved sperm in this. Again, this was just to reduce any of the side effects that the donor oocytes or testicular sperm would have. So here we can see, again, the study occurred from January to March. There were 78 retrievals. The average age was almost 35 years of age. Total number of embryos that were cultured to day 5 was 865. Number of embryos, blasts was on day 5 was 391. Number of blasts on day 6 was 112. So the total number of blasts was 513, or about 59% of the embryos that were placed into culture became blastocysts. Again, this we felt was a very respectable group since there was not, since the patients were of all ages and about 35 years of age. There were 36 patients who had transfers, or 34 patients who had transfers, and the overall pregnancy rate was 55.9%. The other patients that did not have transfers turned out patients who they had all their embryos frozen because they chose not to transfer at that time, or they changed their minds and decided that they wanted to do embryo biopsy. And partly that was because they had more blastocysts than they thought they would have, so they ended up changing their mind. So we were not able to do transfers on all the patients that we thought. But nonetheless, that's a good problem to have. We ended up biopsying quite a few embryos. And the patients that did have transfers, the ongoing pregnancy rates were 44.1%. Again, very respectable. So we were excited with that. So in closing, kind of want to go over this data a little bit here, kind of grouping this in day 2 and day 3, and then afterwards, because it appears that these globulins that were present in the global totals did seem to reduce fragmentation in the media, and it did improve overall blastomere symmetry for the day 2 and day 3, and compaction also seemed to improve in the presence of the globulins. But the incidence of compaction was really high in both culture systems. The proportion of embryos that were 4 cells was over 50% in both groups, and our benchmark in our lab is 50%, so we more than met that in using both culture systems. The day 3 development was also really high, so over 85% of the embryos were at that 6 to 12 cell stage on day 3, which is what we would consider to be normal. We expect embryos to be somewhere between the 6 and 12 cell stage. So that's really the data all the way from day 2 to day 3. So there was some slight advantages from using the globulins. Again, we saw maybe better overall embryo appearance, better compaction, slightly less fragmentation, and better symmetry. But a lot of that beneficial impacts were no longer visible by day 5. So blastocyst development was very similar in both groups. And the proportion of embryos that were of high quality was also there. So it appears that the advantage of these globulins that were present on day 2 and day 3 really wasn't evident on day 5 and day 6. In both treatment arms, blastocyst development combined overall day 5 and day 6 was exceeded 55%, and the proportion of the blastocysts that were of high quality exceeded 60%. So even though there was some statistical significance on day 2 and day 3, the effects of these alpha and beta globulins was not apparent in the embryos by the time they got to day 5 and day 6. So the percentage of euploid embryos was very similar in both groups, and over 50%. So it appears that, again, that the globulins did not improve the ploidy status in this group, in this study. And if you really think about it, we really wouldn't think that these growth factors are really going to change anything. If anything, we would have thought that they perhaps would impact blastocyst development itself, not necessarily ploidy rate. The ongoing pregnancy rates of 69 and 70% in both of those groups were good. And so, anytime you can achieve implantation rates of over 60%, this tends to suggest that both culture systems work very, very well, and that both of them produce competent embryos that can result in high implantation rates. The impact of the globulins, as I stated earlier, were only present on day 2 and day 3. It appears that after day 3, the presence of these globulins do not improve blastocyst development or ploidy rate. The data suggests that both types of protein can support high rates of blastocyst development and outcomes. And really, if we really wanted to further do this, we would have to do a much larger study to see if, say, these globulins are more beneficial for subgroups of patients, say patients who have had multiple failures of IVF, or are there certain groups of patients that may benefit from the presence of these, say patients, for example, with PCOS. We often know that their embryo development can be suboptimal compared to, say, embryos from patients who are diagnosed with tubal disease. So we really would have to delve much deeper into this and create some subgroups to see if there's an impact. But overall, we've been very, very pleased with how embryos develop in the low protein media. We don't see any issues at all segueing out of using the global total proteins, which is supplemented with the globulins, into the low protein media. And in fact, I would imagine that as we get better and better at developing culture medias, that the real impact of the proteins will become less and less. I do want to acknowledge all the lab staff that helped. In particular, I want to acknowledge all the great work that Corey Kelly did. He's our data analyst. He evaluated all of the data and was really helpful in putting together the slides and helping organize all this data in a timely fashion. And I want to recognize our medical director, Dr. Michael Opsel, as well as Dr. Beasley, two wonderful clinicians that without their help, we would not have gotten all these beautiful eggs that we have. Thank you very much, and I hope that you found this presentation useful. If you have any questions, please don't hesitate to email me later on. I'd be glad to answer any of the questions for you. Thank you very much.
Las preguntas que tengáis sobre el vídeo o el estudio de Klaus que tenéis en las carpetas, las podéis canalizar a través del equipo y nosotros se las haremos llegar, y los que estén interesados en ver a Klaus, pues bueno, también lo conocéis directamente, pero ya sabéis que vendrá del 23 al 25, quizás el 22 esté por Madrid, y nada, para verlo y hablar con él ahí. Entonces ahora Steve Levet es el director de embriología en Cooper. Él viene de Life Global, también con una experiencia extensa en el medio, y bueno, va a ser un poco de explicaros cómo se integra, lo que os comentaba antes, cómo se integra el medio dentro de nuestro portfolio de otros medios, con Sage, Orillo, y también va a recalcar otra vez la importancia de todo el tema del pH. Escribió de hecho un white paper sobre el tema de la medida del pH, lo que pasa es que está en regulatorio y no lo hemos podido traer impreso, pero bueno, lo distribuiremos también. So thank you, Steve, for being with us. I'm gonna pull out the presentation.